Okay, so hi guys, welcome to our collab ML session. My name is Alex Lim, and I'm here to run through the codes of the AutoTrader program that we built and we want to improve on. This is a program that we managed to build and experiment on while we were studying the machine learning and the different kinds of neural networks. And we'd like to share this with you so we can work on it as a team and improve whatever we can so that everybody in the group can use this as either a template for future projects or perhaps really use it for trading and make some ka-ching ka-ching, as Momo have said. Okay, so now this program structure was based on a DQN CNN Pong game, which will provide a link for you in the channel, I guess, so you'd know where this project evolved from. So before we start, I'll just recommend for you guys to maybe open a notepad or to pile up your questions or send them in the YouTube chat here. And Momo will try to answer them while I'm streaming, and some of them I will try to answer during and after this live stream. So to start with, please make sure that we all have the same set of files, and they should look like this. Let me remove this. Okay, so if you downloaded it from what Momo gave us in the channel, you should have this set of files. And so we have the Forex DQN, my agent, play best agent, plot progress, the train agent, and the data folder. Okay, just a quick preview of what this does is I'll show you how it's run. So open up your command prompt or your terminal in your Mac, and for me I use the command prompt, and load your environment. For me it's already loaded here because I used the cmd/k conda activate and the name of your environment if you want to automatically load the environment upon loading of the command prompt. Okay, so mine is loaded, and what we'll do is go to that folder. So do a cd folder of where you saved it, and I'll just list down the files to double check. Yeah, these are the files. And I'll just do a python train agent.py. Okay, so what this does is it does a training for the agent. So this is how it looks like. So there will be, of course, your console window or the command prompt where you can see the logs of how it's playing and how it's learning, and how the scores are looking in its progress to attempt to play the best action in the game. Okay, and this window, it's a Pygame window, and what it does is we cut all the noise, and we just plotted the graph, and we did some indication of by displaying a rectangle and a triangle for indicating an open trade, and if it's doing positive profit or a negative. Okay, so I'll just stop this for a while because that's just how we run the program for training. Later on, I'll be discussing how we could use the trained model into letting it play on the best weights that it had produced during the training, after the training. Okay, so I'll close it. I'll just close this down. Okay, so make sure that we have the same set of files, and I'll just open my favorite code editor, and normally I'll just open the folder pointing to that project folder, so I can see all the files here on my left panel. And you can open up your the files forex dqn env myagent.py and the trainagent.py, because these are the three main files of interest during the training. Okay, so just to give you a background, we are using reinforcement learning here to typically, typically an RL setup is composed of two components, basically the agent and the environment. And just to give you a quick concept of that, this is how the concept looks like, where we have one agent, and the agent will do an action on the environment, and the environment will yield a reward and a state, and it will give it back to the agent, so it can learn if it did better or bad on its decision making. So basically, it's just the training is this cycle. The agent will act again. The environment will give out a reward state, and will get the current state and the next state together with the actions, and then it's going to be a cycle. So this means that we are just going to a cycle and cycle the code where the agent will act on the environment depending on the number of the actions that we define. In this case, we have 4 actions, namely buy, sell, sit, and close. And the environment will react on that action by yielding a reward in effect to the action that has been done. Okay. The idea is to determine an action to perform. That's one. So next is get the current state or the current image of the game, and act on that current state, get a reward, and get a new state or the image from the environment, and add all those 4 parameters, the current state, action, reward, and the new state, to the experience table. After which, a mini batch will be selected from the experience table, and that mini batch sample will be used to be fed into the neural network. So again, the code, this means that we are just going to cycle the code where the agent will act on the environment depending on the number of actions that we define. In this case, again, we have 4 actions, namely buy, sell, sit, and close. And the environment will react on that action by yielding a reward in effect to the action that has been done. The idea is to determine an action to perform. Again, act on the current state, get a reward, and get the new state from the environment, and add all those 4 parameters, the current state, action, reward, and the new state, to the experience table. After which, a mini batch will be selected from the whole experience table, and that mini batch sample will be used to be fed into the neural network so that the model can be trained and update its weights. So the next time we use the model for prediction, it can have a better and better choice of actions as the game is being played over time. So having those in mind, let's start with the actual code. Okay, let me just close this. So I hope you guys have opened the 3 main files of interest. Okay, let me just describe the forex dqn env, or the environment. This code essentially defines the structure and the definition of the environment, and this is where the code defines how it behaves, or how it accepts the action, and how it gives back the score. So if you're going to play around with this, just uh, you can change the condition on whatever action, and you may play around with the scores that's been given back to the agent. Okay, so my agent is the file where the structure and definition of the agent, uh, and it also contains the model, which is this one. um, and other functions uh, played by the agent. It will be found here. Okay, as you can see, you will see some commented codes. As you can see, we've been playing around with it, and we've managed to do one setup, and right now we're currently using a convolutional neural network together with LSTM here. So we're not claiming that this is the right setup, but we've managed to get to this point, and we're really wanting the group to be participating in the development, so they could point out the things that we could improve on, especially on the neural networks, on the scoring, and on the conditions of in the forex play response of the environment. So please do so. Get this code, and let's help each other out, and somehow we'll have a good code to work on, and everybody wins. Okay, so this is my agent, and the train agent will be the program to be run in order to train our model by making the agent play on the environment. The train agent program's objective is to produce the best model weights during the training, and will later on yield a .h5 file. So when it's time to let it play what it learned on its own, we run the next file, which is this one, play best agent. So after having that h5 file in the play best agent, we will use that or load that h5 file as an experience of that agent, and it will play based on what it learned. And play best agent, which is just almost the same code as the train agent.py, won't include the randomness anymore, and just using the best learned model weights for prediction based on what it learned, and just plays the best action each game time. Next is the plot progress file, the fifth file. Now this program is used to plot our progress, or to see how good the agent is playing based on the game score over game time. Okay, so you'll see a graph there. Either it's going down or it's going up because of its increasing score or decreasing score over the span of the game time. So, okay, again, heads up on the code, as it may contain commented codes that might mislead you, but just ignore those, because we were just still playing around with the values, so you might.
Can you zoom in the code a little bit?
Oh, sorry. I'll zoom in the code. Yeah, just one.
Yeah, there's.
Or two.
Let's see how it's.
Okay. Okay. So, well, again, I'll just ignore those comments because we were just still playing around with the values. So you might get those in your copy, but we will try to send updates from time to time so you can have a better and cleaner code when that happens. Okay, so I think it's best to start with train agent. Then each time we see a function that's being called from the agent or the environment, we go there and we run through it. Okay, so this is gonna take a while, but please bear with me. So let's open up the three main files at this point. I'll just close the play best agent and the plot progress. Oh, um, before this, I'm just going to show you the uh, content for the data folder, wherein um, that contains our CSV file of the trade data. And it seems that we have uh, from July 13, 2018 data up to February 21, 2019, and it's on a 5 minute interval data. Okay, so this is the OHLC data that will be mainly used for playing the game. Okay. Um, uh, uh, okay, this is located in the folder. Okay, the environment will, what the environment will do is load a record from the data set one by one as if it was an actual real-time trade. So eventually, this can be replaced by the integration with the Forex API and feed the last data that it has and play the real trade. Okay, so let's run through the code and as how it's being run sequentially. So let's start with the main function. Okay, so this is the train agent contains basically essentially two main functions: the process game image and the train experiment. The other one is on line 148, the main function, which is just being called when you run it. So that's the first thing that's being run. Run the main function, then we go to the definition, and under the main function there is a train experiment function. So we go to the definition of the train experiment function, and this is essentially the heart of the training program. Okay, so what you guys will see is just on the first few lines of code is just the initialization of the variables and the instantiation of the agent in the environment. So we set the train time to 0 and the train history to be a blank array, which will be later on used for it will contain the score and the game time to be plotted in the pie plot. Okay, and the score check is a deck data type. A deck data type is an array essentially, and it's a very fast when you want a fast processing of an array wherein you append in the right or in the left, or pop left pop right. Deck is the best data type to use if that's how you process the arrays. So in case of the score check, we'll be continuously adding scores to the right, and we're gonna pop the ones on the left. Okay, so that's that. And not we have a not quit variable initialized to true, because that's one of the conditions in order to continue or stop the loop. So if you could see here, we just jumped on line 76 where the while loop is. There's a not quit there. While the not quit is true, it will still continue to run the training. But if some part of the program made it false, then it will stop the training. And later on, we'll get to this point. But going back to line number 50, we go to line 55 now. So this one is the instantiation of the environment. So for us to do that, remember the environment is on the forex dqn env, and the agent is on the myagent.py. So for us to make use of the functions and the classes inside it, we have to import it using import forex dqn, which we
Move this to the
oh, sorry.
left, make it a little bit smaller.
Okay, I'll just move my uh, video here and make it smaller. Okay, so in order for you to make use of the functions inside these and the classes inside these, we can just do an import and the file name without the .py. And it's up to you if you're going to create an alias for you not to type forex dqn env over and over and just refer to it as myforex. In this case, the forex dqn env has an alias of myforex, and import myagent doesn't have an alias because it's short enough. So that's how we instantiate it. We go back to line 58. Well, where sorry, 55. So we create a variable that instantiates uh, a class inside myforex. So if we go inside uh, myforex, which is referred to the forex dqn env file, there will be a class there that's named forex game, and all the attributes that it was set in here is going to be instantiated using this. So you assign your variable to the module dot class, and that's how you instantiate the environment. Same goes with the agent. We just refer to the module dot the class, wherein we could check here there's a class agent. So once that's coded in, it will immediately instantiate it to the variable the agent. Okay, so anything that we'd like to do or to use inside of these the agent or the environment, we just refer to it as the game and the agent here in this train agent file. Moving on, we also have the best action set to 0. Okay, this will be later on be the values for this best action will later on be predicted by the agent, and right now it's just an initial value for us to have something to start with. Okay, and then we play a next move based on that best action, which is right now it's 0, and then that play next move is from the environment, which is here, and you can find it here on line 271. Okay, wherein inside the class there's a function that you can we can utilize to perform these codes inside it. So play next move has the parameter of the action, and that's what we're doing here in the train agent. So we're sending that action to the function, and ultimately it will yield a score and an initial screen image. Okay, and we can see that in the environment, in that function. At the end of that function is a a return. So it returns a score and a screen image. And later on, I'll discuss that part where it processes that before it gets the score and the image. But this is just for the initialization. So it will use that initial screen image and the initial score. And this is where we will use the process game image because the window is quite large in the Pi game. And we'll just process that image by sending the initial screen image to this function, wherein this resides here, wherein it just using SK image to convert the RGB image to a grayscale. So when you pass that parameter, it will process that raw image and convert it to gray image. And yeah, you can see here how we played around with the shape and the cropping. You may choose to do that when you're playing with it, but right now we just converted to grayscale and resized it. We resized it to this size defined on a variable called image height and image width defined up here. So you may also play around with this. Right now it's set to 80 height and 80 width. Okay, so basically that window that you saw when I played the program a while ago, it will resize it to an 80 by 80 size. And then the reduced image will be that 80 by 80, and it will return it back here, which is this one, line 65. So the reduced image now is in initial game image. And now we defined the model using Keras to expect a shape of currently we are using 1 by 80 by 80 by 4. So for us to convert that image into that size, and actually we're stacking up four historical images, or rather previous images, and that's what we feed in the neural network. So, and in this case we're just initializing it. So the initial image will be stacked 4 times, as you can see here, and this stacking will yield 1 by 80 by 80 by 4, and just to make sure it's been reshaped into like so. So it's going to be a 1 by 80 by 80 by 4 here at this point, which is the game state. Okay, now we enter into the training loop. Okay, so what this does is it checks the condition of a while ago I talked about the not quit, and if some part of the code makes it false, it will go out of this loop. Otherwise, it will just continue. And the other condition is when the environment variable called current data position, which is actually initialized upon instantiation, from here, let's go to the init. Okay, upon instantiation, it runs the init of that class, and the current data position right now is 0 upon starting. Okay, so what this means is if the data position is still not equal or still less than the total length of the data that we are feeding it, it will just continue to run the loop. and also check on the not quit, because we might be getting a high score already, and we don't need to exhaust the whole data set of our trade data. Okay, so inside the loop, we uh, execute the find best action using the game state which we initialized a while ago, because later on, uh, after making one complete loop, the game state will come from here, the next state. So it will just be a loop of iterating over the next state to the next. Okay, so it will find the best action, and it will be saved on the best action variable. Now the find best action, um, we go to the my agent, because it's being it shows here that it is a function of the agent. So I go to my agent, and I'll just scroll down here to go to the find best action. Okay, so what this does is, um, depending on the observation period, and depending on the epsilon, it will try to return a random action based on what we defined, based on how many we defined as a number of actions, wherein this NBR action is defined here on top, which is NBR actions 4, which is the equivalent of the buy, close, sell, and sit. Okay, so it will randomize a number between 0 to 3, because number of action is 4, so we add a -1, so it can choose a number from 0 to 3. If the observation period, if the steps are still less than the observation period, that's the exploration function of behavior of the training. Okay, so either the steps are still low, and the observation period, by the way, is also set here on top as a 50. This is quite low, but for testing purposes, this is you can see it switching from randomness to prediction if you set it low. But if you want to try it on a higher observation period, please do so. Okay, so either a random number is less than the epsilon, meaning it's less than 1, because the epsilon is initialized as 1, and we can find that here. Class agent epsilon here, this is 1. Okay, so either the random number is less than 1, or the steps is too low, not going beyond the observation period. It will still do a random number from 0 to 3. Else, if the steps goes beyond the observation period, it will start predicting from the model. Okay, and we pass that state here. We go back to the train agent. We pass the game state in the find best action. So in here locally, it's being referred as to S. So we can start using the predict function of the model, and through that state of the image, we can get a Q value. Okay, a Q value. Let me just type in here a Q value based on our definition in the model. It will yield, since we said the number of actions. Let me just go to that code. Yeah, we created in a model that we defined that the number of actions in the final output is 4. Okay, so it will be corresponding to the 0, 1, 2, and 3 for uh, sit, buy, sell, and close. Okay, so it will yield, when you predict, it will yield a number like this. So this corresponds to the sit, uh, buy, sell, close, respectively. Uh, when it predicts a high score for the sell, respectively, that will be the chosen action. So what happens here is the Q value will look like this. So we have to determine the best action as a numerical value corresponding to 0, 1, 2, and 3. And those are the indices of this array, which corresponds to sit, buy, sell, and close. So in order for us to do that, we do an argmax. What the argmax does is you pass in this array, and the argmax will get the index of the highest value. So in this case, in my example, the index 2 will be yielded from the argmax because it is the highest in the value of the actual value of the element. Okay, so that 2 will be returned to the variable best A. Okay, let me just remove this. Okay, so that's how the prediction works. It predicts, yields a Q value, and get the index of that highest value using argmax. Okay, so we go back to train agent, which executed the find best action. Okay, so remember, it returned a best A here, or it returned a random number from 0 to 3. Whatever it was, it's going to be stored here in the best action on the train agent, and that best action will be used to be passed in the play next move. This time, it's based on finding the best action, either a random or prediction, not like before that we play next move using an initial value. So that's going to be the loop here. So again, it will yield a screen image and return a score. Okay, let's go to play next move first, and it will be on the environment. So I go here and I go to play next move. I'm going to look for def play next move, where the first parameter is the action, which we passed here. Okay, and the environment has a variable called current action. Okay, and it will the action that's been passed will be saved on that current action. It will just print it out, initialize the score first before any condition modifies that score later on. Okay, so what this does is we have this variable called current data position. So every time it loads data from the data set, from the trade data, it's corresponding to one data position starting from 0, and every time it sends in a new record or new data from that data set, the data position will move along with it. Okay, so this means this just means that this is a condition if the position is greater than the max data view width, which is we limited the display on the graph to 100, I think. to 100, let's check. Max data view width is defined here in the initialization of the class. Which is on line, yeah, here, 103 of the environment. Okay, so what this does is we set a maximum limit of how many data to display on the graph, because if we display too much, it's gonna squeeze in so many. Well, for what we have now, we have 65,000 records of trade data. So each time it reaches 100, it will move to the last 100 and display that graph on the screen. So what? Let's just go back to the play next move. So okay. So going back here, this just what this does is select the last 100 and set that selected range of 100 to the current data. Okay, so what the self.data contains all of the records being loaded from the CSV file, and we can see that as well on the initialization of the environment, wherein this is the self.data. So we used pandas to read the CSV from this directory and from this file. So once that's been read, all the 65,000 is contained within the self.data. And later on, we're going to select 100, the last 100, each time it feeds in the data. That 100 will be contained in the current data. Okay. So again, let's go back to the play next move. So what this does is, because the play next move essentially will just plot the 100 range, the last 100 range from the data set, and show it on the screen. So for us to prepare that, it's we're gonna take a part of self.data and just select the 4 columns, and in this next index is let me just copy this and explain it more. What this does is it should be yielding a number here, which is a range from, like, if we want to get, if the current data position is at 100, and we want to get the last 100, so it should look like this, 0 to, well, 99. So if we want to get the last 100 records, sorry, for if the current data position is 100, it should be 1 to 100. So what this does is dynamically compute the values to be on this range. So what this does is, if the current data position is continuously moving upon feeding of the data, let's say the current data position is let's say 200, and we have the self max data width. A while ago we saw it to be 100. So if this data position minus the max data view width is put there, it will look like 200 minus 100, which will yield to 100. Starting from index 100, it will then get the data position, which is 200. So here, it's gonna be put here, which means from the overall data, we just get the four columns and get the last 100 data. Okay, so that's how this code works. And if the data position changed to 201, it will look like that's 201 minus 100 is 101, and 201 200 will be 201. So it's moving by 100. Okay, so that's just what it does, selecting the last 100 records out of the out of the one by one feeding of the environment from the data set. Okay, so let me just remove this. Okay, once we have the last 100, well, again, let me emphasize that this will be the last 100 will be captured when the data position is higher than the max data view width, which is 100. But if it's less, it's just gonna start from 0 here, 0 to the data current position. So it's, if it's 40, it's gonna just going to get a data range from 0 to 40. So that's just essentially this block of code. Okay, and if we get data from that range, which is when the current data is not empty or none, we can now start plotting it. Okay. For this, the environment also has the current data variables, which is the current data date, current data open, current data high, low, close, volume, preparation. So we didn't really use this yet, but it's there and it's been saved in memory in case we need to utilize it. But right now I think we're just using the data close. Yeah, and just the data close. Okay, so after getting the last 100 or less than 100, we just select again the open, high, low, close, and assign it to the current data OHLC, which is the requirement for the candlestick OHLC function from the MP Finance or MPL Finance module. Let's take a look. On the topmost, it's been initialized here. Yeah, the candlestick OHLC is a function inside MPL Finance module. So that enables us to graph it using candlesticks. So let me just go back to, sorry, I passed it. Play next move. Okay, the candlestick. Okay, so what this does is it well, upon initialization of the environment, it created an axis using pyplot, and it's just telling this candlestick OHLC function to plot this current data OHLC values that we prepared just above it, and plot it on the axis that's been initialized during the initialization of the environment, which we can see here in this part. Okay, so the PLT here is from the matplotlib.pyplot, so it's a pyplot. So the plot subplots here prepares an empty graph wherein we can refer an axis inside that graph and utilize it later on, and that's what the play next move is doing. So we go to that part again. Sorry guys if I scroll too much, but yeah, we're referring to the axis of where PyPlot initialized it during the initialization and graph the OHLC values. So, and then again, this is a Matplotlib, which has its own module or window to plot on. Again, I need to emphasize that we're using Pygame here, and Pygame has a separate window to interact on. So we were plotting this in the background in Matplotlib live, and for us to get the graph, we need to create a canvas, and it seems that it needs also a renderer for us to convert the image plotted to an image recognized by Pygame. So once that's converted into a recognizable image, then we can display that into the Pygame, which what this does. So from the self image here, we feed it to a self. The self image is fed in here in this function to be to be a recognized RGB image. And what we do is we fill up the screen with white, and then load that converted image to the Pygame. So this blit function enables you to display images on the Pygame. Okay. You can browse around about Blit in Pygame documentation. And just to move forward, at this point we already displayed the graph in Pygame. And remember we had those rectangles and triangles on top. Those are just our indicators when an open trade has been opened. A trade has been opened. Whether it's a buy or a sell, we display a rectangle. And the rectangle moves, if it's a rectangle on the left, it's a buy. If it's a rectangle on the right, it's a sell. And if we display a triangle pointed upward, it yielded a positive profit from its trade. And if it's a triangle pointed downward, it's a negative or a zero profit. So this is just for indications that we thought that by using these indicators, we could somehow teach the model to recognize if it's a buyer or seller, or if it's doing great in terms of image. Well, at least that's the concept. Okay, so we really need you guys to join in, and I'm calling out on the experts on CNNs, and just tell us if we're on the right direction here. But somehow we managed to get results from this. Okay, so after graphing it, we need to do the trade action, because this is just graphing the last 100. And what this does is this determines the score. The trade action function is the heart of the environment, actually. So we know that the action has been passed here at the first line of the function, which is the self current action equals action. So we know that the current action being played has already been saved in the current action. So when we execute a trade action, inside this function, it will utilize that saved current action variable, and will be the basis, one of the basis of yielding a score. Okay, then just to continue, because this just a few lines left before we go diving into the trade action part. It once it yielded the score, it just updates the pie game display, and this is just for quitting the game. And um, let me just, yeah, sorry. So after processing that, the graph, it will add the data position to a +1, making it adding a 1 on the last data position. And this one is just for controlling the speed. Right now the game speed is set to 0, so there's no delay. If it's too fast for you, then you can just adjust it on the initialization on top of the code. So the game speed is in terms of, I think, milliseconds. Okay, so what it does is next is we get the display on the pie game window and put that in the screen image. So thus, essentially, the play next move function is just to yield the screen image and the score. So we already know how to get the screen image just by doing this, and the score will be determined from the trade action. So that's the end of the play next move. So let's go dive into the trade action. Okay, the trade action function is right here. Okay, line 129. Okay, so remember, every play move we're saving the action to the current action. So here's where we utilize this as a condition to perform to determine the appropriate score for each play in a game time. So this is where you can also experiment. When you get this code, you can play around with the scoring and the conditions here. But right now, I'm just gonna explain what we have. So right now, we're just checking the condition if the current action is a sit or the current action is a close. Let me just give you an idea where the sit and close are defined here. So we go up here, and in line 43 to 46, the action definitions are set here. These are just normal variables. So when you see a sit, buy, sell, close, it's just corresponding to a numerical value from 0 to 3. Okay, and so this means if the current action is a 0 or 3, it will go inside this nest. Okay, it initializes, just to play safe, we just put the score to 0, because later on it will be overridden by the other conditions. So what this does is, if it's a sit or a close, it will do this. Else, if it's not a sit or a close, and it's a buy or a sell, it will go to the else part. Okay, so let's just start having in mind the current action is sit or close. Okay, but before that, let me explain to you the difference between the current action and the open action, which you can see here, current and open. Okay, every time it does a buy or a sell, it records that into the memory by using the open action and saving the open action on that moment that it was opened through a buy or a sell. So wait, let me. Yeah. So the the open action is our indicator to tell the agent if there is an existing open trade, and it tells us the status whether the open trade is a buy or a sell, or sometimes it's equal to close if there's no open trade. So there's three values for open action: buy, sell, and close. Okay, and the current action is the action currently yielded from the prediction. So the current action can have values like buy, sell, sit, and close. But the open action is at the moment it opened, it will just save whatever status that is, whatever action that is, and just save it in memory, because later on, well, we need to go back and compare it if the current action is appropriate according to the whatever open action it was. So that's the condition actually in the next line. So when the open action is previously a buy, and you're doing currently a close, we compute the pip difference of the current data close and the open data close. Every time it opens a trade, it also saves the the open high close data into these data variables. Let me show you. Okay, when we initialize the class, we have these sets of you can see the current data date, current data open, current data high, low, close, volume, and we have here open data date, open data. So initially these are populated by the starting point of the data set we have, and the open data is set to 0. But once we open a trade, this will become populated, and it will remember these the values of these data on the moment that it opened it. So later on we can compare the open data close compared to the current data close. Okay, so it's like I don't know if I made an Excel for that. Check. Yeah, not this one. Okay, so this is going back. We're just determining the difference of the current minus the open data close, wherein this is the close value on the moment that it opened, and determining the difference between the current one and the moment that it opened the trade. So that's the difference, the pip difference, and this is normally a decimal value. So we have the pip unit multiplier set to 10,000. So later on, the pip difference would be multiplied by the pip unit multiplier as an added score that will be yielded in this trade action. So the positive reinforcement here is set to 1. So it means that when it does a buy and a close, we're rewarding it with a 1 point plus the pip difference. Else, if the pip difference is not a positive value, we just get the decimal point of it, and it will still yield a positive value, but as compared to a 1, it will be a decimal value, so it will somehow teach the model to have weights. Uh, Both are positive, but the other one is greater than the one with the lesser difference. So okay, so I need to hurry up, I think, in this part. So this is just determining the score for the buy and close when it does a buy and close, and the fact that it uh, did a close on the current action, it's closing also the open action and setting the open data set to 0 again. Okay, when it does a sell and a close, uh, open action sell and then current action close, it will do again that computation, but yeah, still having that, we want that because we want a sell, then it should learn how to close eventually. So this is also the same, and we just log it in the console by using the print, and we draw, actually we draw the triangle here. This is just drawing the triangle. Draw computed profit indicator if it's positive or negative or 0. This is also being executed in the buy close. So we have the buy close, sell close, and the close close. We don't want that. It needs to learn not to close when it's already closed. So we put a -1 in the score. A buy and a sit is, well, this is debatable. Last we played around with, we don't want to for it to have a positive score, because we don't want it to learn to sit, because it's okay with that. We don't want it to sit for too long, and we had a run before that it's just okay to play sit, because it's already yielding a score of 1. So we don't want that, but not really. That's why it's 0.5 and a negative. So feel free to play around with this, and that goes the same with open action sell sit, and the close sit is a -1. Okay, and then if the open action is already a close, may it be may the current action be a buy or a sell, but the open action is close. So we want that. If it's if there's a no open trade, we want it to open by itself. So this is what the code does, and it populates again what I've explained to you before. When it opens, it records the current data for that position into the open data variables, and it saves that into to the memory for later decision making. So we want that. It opened a trade, so it scores 1 here. If the open action is a close, yeah, we can do that. But if it's already opened an action and it opened again with a buy or opened again with a sell, we don't want that. So it's a -1 here. Okay, so that's about it for the trade action, and we just return the score that yielded from this kind of behavior. So feel free to modify this, because we need to improve the behavior of the environment. So this determines the score. Okay, so the play next move again, which called the trade action, will return a score and an image. So we go back to the train agent, which called the play next move, and we caught this score and the new screen image, and we process that image. And what it does is just do a grayscale and resize it to 80 by 80, and assigns that to new game image. And again, we need 1 by 80 by 80 by 1. So we reshape that image into that shape, and again, we're feeding it four images at the same time. So we use that new game image plus the last three previous image, and that becomes the next state that we will be feeding into uh, the the network. So this is just that. Then after we get the source, as they call it, the state, the action, the reward, and the next state, we will pass that into the capture sample function, which is in the agent. So we go to my agent. The capture sample is just populating the experience replay for later to be used in the process function. Okay, so let's just do this. It just appends that sample that we passed the source into the experience replay, and as long as the length of the experience replay is not well, if it's exceeding the maximum capacity of the experience replay, which is set to I think 5,000. Let's check that here. Yeah, it's 5,000 here. So it means you have a 5,000 data set for the experience replay, and once it goes beyond that, it's gonna pop left the last data. So we retain a steady, a solid 5,000 experience replay, and it adds a step for indicating the epoch step, and this this is the part where it you can play around with this. This is the epsilon decay function. When the step goes beyond the observation period, the epsilon will be updated to 0.75, or the steps, if the step goes higher than 2,500, it's going to be 0.5, and so on. Thus, as the game time increases, the epsilon decreases, and later you'll see the effect of the epsilon in its prediction, whether it's going to be a random or based from a prediction. So this takes a real a significant part in whatever it's going to behave in terms of prediction. So that's just the essential part of it. The capture sample is populating the experience replay and updating the epsilon. Okay, so going back to the train agent. The next line would be the agent's process function. Okay, so when we go to that, it's just below that capture sample function. Okay, this is the heart of the training. Actually, this is where it determines if the model is going to be trained or not. So if you can see here, if the steps is going beyond the observation period, what it does is it takes a random sample out of the experience replay and gets a number of data range, which is the batch size, and the batch size is I think defined here as a 32. Yeah, a 32. So what this means is, sorry. What this means is, from the experience replay of 5,000, you get 32 out of those 5,000, and the random sample is just getting any random position and gets 32 out of it, and assigns it to sets it to the mini batch. So the mini batch contains the 32 samples of that experience replay, and the batch length will most likely be a number 32. Okay, and the inputs and the targets will be used for, let's jump into the model fitting here. The inputs and the targets will be used here for training the model. And we initialized it here as zeros at first. And then from that mini batch, it will loop and prepare the values for the inputs and the targets in order to be fed in the fit. So basically the inputs here are the X values, if I'm not mistaken. If I refer to the definition of the fit here, yeah, it's still loading. The inputs are the X values, and the targets are the labels. I think I prepared a sheet here for visualization. So the experience replay here is like this. It's from 0 to 4999, and it will contain the SARS, the SARS. Then it will get a mini batch of 32 from 0 to 31, still with the SARS, and the inputs based from the code is 32 by 1 by 80 by 80 by 4, and it will contain the image of this dimension, and the target will contain the inputs have 32 records, and the targets also have 32 records, but different values. The inputs have images, and the targets have the values for the sit, buy, sell, and close. And it seems that that's what's going to be used for feeding it to the model for training. Then it updates its weights, and it will loop back to, well, that's the process. It will just, after this, it will just repeat the same cycle. So until it proves its weights and does the same thing, and eventually we can see the graph from going down, making mistakes, and improving its predictions each game time. Okay, so well, what this does is just increase the train time, and every 5,000 train time it saves the weights, and every 100 train time it's just prints it out on the screen and appends the time and the score in the train history that I mentioned a while ago for plotting, and it will just save that those files, those data into trainhistory.dat. That's a file name that the PyPlot is going to use for showing the progress of our score versus game time. And here it just appends a score. When the score is above the score length, it pops it left, pops the data from the left, and when this one just gets the sum and the average. If the average is greater than the target score to end the game, it will now trigger the not quit to false. So this just means that even if the data set has not been exhausted, but the score is very, very good, it will trigger not quit to false, thus ending the loop of the training. Yeah, I hope this jumpstarts our group into going deeper into machine learning, and I hope everybody participates in the continuous improvement of our project.